All right, let's go ahead and get started. It is 12:10. So, just a reminder, I have office hours after class, Monday, Wednesday, Friday. Today, they're over in CAD in the South Silo. If you want to come help, I'll be there from 1 to 4. If you want to come get help, I'll be there from 1 to 4. You can also help, I guess, but um, so some limits of functions of two variables here. I will point one thing out that I've observed is that typically, if you're not approaching 0, 0, typically, not always, but typically, usually if you're approaching something other than 0, 0, usually that limit's going to exist because it's harder to find a bunch of pathways that go through that particular point, right? Where it's a lot easier to find many, many pathways that go through 0, 0. So here, this one does exist, and we can see that if you plug in 2, 1, which is what we should always start with these kind of limits, just like any limit, right? We plug it in, see what happens. To plug in 2 for x and 1 for y, I think we're going to get 0 divided by 0, right? 4 minus 2 minus 2. Yep, that's going to be 0. And 6 minus 6, that's also going to be 0. So if we plug it in, we plug in 2, 1, we get 0 divided by 0. Usually that would mean for us that we try to find different pathways to see that the limit doesn't exist, because that's most of the time what's going to happen, but not always. In this example, this expression here, both the numerator and the denominator factor. And actually, I think factoring the denominator makes it easier to see what we're looking for in the numerator. So we factor out the denominator. Well, we really just pulling a 3 out. So you got 3 times x minus 2y. And we can see that that x minus 2y part is the part that's making it 0 in the denominator, right? If we plug in 2 for x and 1 for y, we get 0 there. So that means I probably need a similar factor to show up in the numerator. So I'm just going to pretend like it does. I'm going to say, great, I have to have an x minus 2y multiplied by some stuff here that's going to multiply out to that. So let's see. It looks like I need an x here. So the x times x is x squared. And it looks like I need a positive y over here. So that negative 2y times positive y is negative 2y squared. And if we check the middle terms, I get a negative 2xy and a positive xy. And those add up to a negative xy, which is my middle term. So this is, in fact, how that numerator factors. You could FOIL it out if you wanted to see yourself, but it does equal the thing that was up here. So great. That means then I can cancel, or I should say the x minus 2y and x minus 2y divide to 1, and we're left with the limit as x comma y approaches 2 comma 1 of just x plus y, which we're then just going to plug in 2 for x and 1 for y. Oh, I forgot the 3 on the bottom there. Sorry about that. X plus y divided by 3. And we're going to get 3 divided by 3, which is 1. And that's our limit. So occasionally these exist. A lot of the time they don't exist. So let's look at this other one. Usually they won't tell you, right? Usually they'll be like, evaluate the limit or say it doesn't exist. They're not going to usually say this one exists, this one doesn't. They're going to be like, here's a limit, tell me what's happening. So we're told this one doesn't exist, so we have to find some pathways through 0, 0 that are going to make it have different values. I always recommend picking either, or sometimes even both pathways that are y equal to 0 and x equal to 0. Those are kind of the go-to places to start. So if we try setting x equal to 0, we're going to get the limit as y approaches 0. I'm not writing the x anymore because we're saying x is equal to 0. So now we're only concerned with y getting closer and closer to 0. That's why I don't write the x there. Limit as y approaches 0 of 8 times 0 squared times y divided by 0 to the 4th plus 3y squared. Normally I would skip writing that and simplify it on demand and just say, yeah, I've got the limit as y approaches 0 of 0 on top divided by 3y squared on the bottom. And this is the important part that I think we covered last time, but I'm going to say it again. We don't get 0 over 0 here. Y is specifically not 0, right? It's getting close to 0, but it's not 0. And 0 divided by not 0 is 0, right? 0 divided by 5 is 0. 0 divided by 7 is 0. 0 divided by 0.00001 is still 0. So if you got a 0 over not 0 on the bottom, you're taking the limit as y approaches 0 of 0. And then you get to say the limit of a constant is just whatever that constant is, which in this case is 0. But now our job is to find a different path that doesn't result in 0. And that's where things get more challenging. Yeah.
Can you explain one more time how you just chose x equals 0 and then change the limit to just y equals 0?
Sure. So what we're really saying here, and I should use more paper. what we're saying is in fact, I'll show you a graph of this in a second here. But what we're really doing is we're saying this surface looks something like this, right? I don't know what it looks like, but we're saying we're going to approach the origin along the path where y is always 0. So we're coming at the origin along this pathway where y is 0. So, and on that line, y is always equal to 0. So we're just going to replace y with 0. It's no longer that y is approaching 0. We're setting y equal to 0. And then we're saying, let's see what x is doing. We're going to make a different choice in a second. There's something else I want to say here. The only restriction is that your path, your curve, your line, your parabola, whatever it is, has to go through the point that x comma y is approaching, which is why the origin is usually so nice, because there's lots of different functions that go through the origin that are easy to come up with. So let's look at another possible choice. So I'll point out that if we were to choose y equal to 0, which is this pathway, right? That's oh my gosh, I said the wrong thing. It's terrible. Sorry, we just did this one. So I will point out, and I'm sorry for potentially confusing you because I was saying the wrong thing. This pathway here is x equals 0, right? The y-axis is where x is always 0. We just did that one. Now we're going to try y equals 0, which is the x-axis. Sorry about that. I apologize for misspeaking there. So along the path y equal to 0, we're going to see a similar thing happening. We're going to get the limit now as x approaches 0. And if we plug in 0 for y, we're still going to get 0 on top. And we're still going to get, we're going to get x to the 4th plus 0 on the bottom. And just like last time, 0 divided by x to the 4th is still 0. So we have the limit as x approaches 0 of 0, which is 0. So it didn't help us, right? Because as far as we're concerned, both pathways have shown us that the limit value is 0, but we've been told the limit doesn't exist, meaning there's got to be some path that doesn't end up having a value of 0. Let's try something else. Let's try the path y equal to x, which is this line right here. We're going to approach the origin along that direction. So if we do that, let's see what happens. So you can either replace x with y or y with x. Either way is fine. I'm going to write it with x's because that's typical. So I'm going to say I have now the limit as x approaches 0. And my expression here is going to be 8 times x squared times x over x to the 4th plus 3x squared. So simplifying this, actually what I'm really going to do is I'm going to factor out an x squared from the bottom. So I have the limit as x approaches 0 of x squared times x squared plus 3 on the bottom. On the top, I have 8x cubed. I cancel as many x's as I can. So I cancel an x squared there and 2 of them there. I'm left with the limit as x approaches 0 of 8x over x squared plus 3. And then if I plug it in, I get 0 divided by 3, which is 0, which doesn't help me. And the issue with this is that you can kind of keep trying a lot of different things, and it can be difficult to stumble upon the correct pathway that gives you a different value. Bless you. So what I usually look for when I'm trying to make this work is I'm trying to look for a pathway where, I'll say this the right way, where the highest power of the variable that's left, either x or y, is the same in the numerator and the denominator. Actually, they kind of all have to be the same, not even just the highest power. I want them all to be the same. So if I look at this initial expression here, I can see that I let y equal x squared, things are going to work out the way I want them to. Let me show you what I mean. So along the path y equal to x squared, which just for your graphical purposes, now we're taking this path. Still goes to the origin, so we're still good to go. We're going to write the limit as x approaches 0, and we're going to replace each y with an x squared. So we get 8x squared times x squared over x to the 4th plus 3x squared squared. And now look what happens. We get the limit as x approaches 0 of 8x to the 4th divided by x to the 4th plus 3x to the 4th. We can add those together and get the limit as x approaches 0 of 8x to the 4th divided by 4x to the 4th. X to the 4th divided by x to the 4th is 1. 8 divided by 4 is 2. So we're left with the limit is x goes to 0 of 2, which is 2. And that's a different value. That shows us, since these aren't, since this 2 is different than any of those zeros, right? Not the same. That shows us that the limit doesn't exist. So we can conclude limit x comma y approaches 0 comma 0 of this original expression 8x squared y over x to the fourth plus 3y squared does not exist. Let me show you, because I think it is kind of cool to see what's happening here. I'm trying to do that the wrong way. 1 second. Sure. Let me grab this graph. Let's see. So we have, what was it? 8x squared y divided by, where'd you go? X to the fourth plus 3y squared. I don't love that color. 1 second. Go away. So here is what that surface looks like. And if you zoom in towards the origin, it kind of starts to look super funky there, right? It looks very bizarre. So let's look at some of the pathways. I'm going to go back to the standard view here. So okay, fine. Sorry. So we look at some of the pathways we looked at. Well, here's, say, y equal to 0. I would like a different color, please. Why would you give me that same color? Who makes these decisions? Okay. And so you can see that, yeah, along that pathway, the values are 0, right? We're just getting 0 the whole time. And similarly, let's just change that. Along the x equals 0 pathway, we're also, where that plane is intersecting that surface is all just values of 0. It's kind of harder to see, but you can kind of, right? You can see it's 0 there. You can see it's 0 there, right? The surface is always 0 along that line. You can even see it along the line y equals x. Oh my gosh, not if I do that. So there's the line. Let me extend it again. Maybe, maybe not. There we go. So along that line, the function is still equal to 0. The surface is still equal to 0. I feel like it's harder to see that one there, to be perfectly honest. That seems a little bit funky. Maybe they can't be, maybe I think we're not getting some negative values, but like over there, I don't know if I buy that. It doesn't look like it's, I guess, but when we get close to the origin, right? It wasn't 0 all the time, but when we get close to the point of the origin, it is going down to a value of 0, right? It's, you can kind of see it's traveling down right there to getting to 0. However, along the pathway of y equal to x squared, check it out. The values are 2 the whole time. And so when it's coming at the origin, it's getting closer and closer and closer to the origin. It's still 2, 2, 2, 2, 2 the whole way through. And since the different directions have different values, the overall limit doesn't exist. Wild things are happening at the origin here. So that's why we're doing this. That's why, or that's, I should say, why we're allowed to show that the limit doesn't exist this way, by finding different paths that end up giving you different results. So what I would say about this is, when you're doing a problem like this, that means it's not enough. You can never say a limit exists by just trying one more path. That's never going to be enough information to show a limit exists. To show a limit exists, you either have to do some factoring thing or something else, which we'll talk about in a minute here. I want you all to try this next one. Yeah. So this one's going to be slightly different, but same idea. I want you guys to show that this next limit also doesn't exist. Yeah. Both. So the reason I picked y equal x squared here is because I could see that when I plugged that in, the power on top was going to end up being 4, and the power of both the terms of the bottom was also going to be x to the fourth. And that was going to allow me to simplify things in a way where the x to the fourth power is essentially canceled out.
Does it kind of just like you look at the problem and try and just pick the best?
Right. You try and guess some stuff. I would also say you should always start by using x equals 0 or y equals 0. That is always a good path to try first, because it almost always, not always, but almost always gives you a value of 0. Question?
Is this like all like trial and error?
Yes, it is all trial and error. How exciting. Until you get two different values, which shows that the limit does not exist. Correct. You might be wondering how you show the limit does exist. We'll talk about that in a second. So why don't you all try this one? The limit as x comma y approaches 0 comma 0 of 3xy cubed over 5x squared plus 2y to the sixth. And I would encourage you to start by trying x equal to 0. Yeah. Right. You can choose any path as long as it contains what point? The origin, as long, well, I mean, or whatever point we're approaching. But yeah, you can choose any function that goes through the origin. So try a few things. Bummer. Anyone have any bright ideas?
Put a y cube.
Try that. Try x equal to y cubed. The limit as y approaches 0 of 3y cubed times y cubed over 5y cubed squared plus 2y to the sixth. Yeah, those powers are all going to match. We get the limit as y goes to 0 of 3y to the sixth over 5y to the sixth plus 2y to the sixth is 7y to the sixth. Y to the sixth cancel. We're left with 3 over 7. And that shows us that this limit doesn't exist. But you can see it can be somewhat challenging to find the correct path that's going to give you something else. What I'll point out is for expressions like this, especially, if you make a path choice and you end up with a mismatch in powers, you're going to get 0. Right? If all the powers aren't the same, it's never going to work out because you have to factor something out from the bottom or from the top, and then you cancel that out, and then you're left with 0 over not 0. Typically, is how that usually works out. Yeah, almost always. So you're really, really, really looking to get a match in the exponents for all the x's or y's I'm left with. It can be kind of hard to see sometimes. One more non-existing one, we'll talk about one that exists. Sure. So let's look at this one, which doesn't go through the origin. Where'd you go? There you are. The limit is x comma y approaches 1 comma 1 of x plus y divided by, 1 comma negative 1, apologies, of x plus y over xy plus 1. If it was 1 comma 1, it'd be easy. It'd be 1 plus 1 over 1 plus 1. We'd be done. But it's not. It's 1 comma negative 1. And if you plug it in, you get 1 minus 1 over negative 1 plus 1, which is 0 divided by 0, which is, wow. So when you're doing a limit like this, I would always encourage you to approach it with the expectation that the limit's not going to exist. Because usually no one's going to have you do one that exists this way, because it can be terrible, right? Like you have to try a bunch of things and they're like, well, I think it might exist. So now let me try doing some other stuff. So usually if you're given limits like this and it doesn't if it doesn't factor easily or just plug in and have a nice value already, it's probably going to be a non-existing sort of situation. So since I'm not going through the origin, I have less options in my opinion. I would always encourage you to choose the options that are x equal to the value that x is approaching or y equal to the value that y is approaching. So in this case, let's try the path where x is equal to 1, because that's the value that x is approaching. So let's see, we're going to have the limit as y approaches negative 1, because x is already always 1, of 1 plus y over y plus 1. Well, that works out nicely. 1 plus y divided by 1 plus y is just 1. That's the limit as y approaches negative 1 of 1, which is 1. So now we're just hoping to find some other path that goes to this point, 1 comma negative 1, that doesn't have a value equal to 1. There's a couple of choices I might make. I would probably try choosing y equal to negative 1. Another plausible choice would be y equal to negative x. That's a line that does go through the point 1, negative 1. But let's try y equal to 1. So if we do that, we're going to get the limit as x approaches positive 1. And then we have 1 plus y over negative y plus 1. I feel like I'm making this. No, I'm doing something stupid. What am I? Oh my gosh. I'm ashamed. I'm embarrassed. No, it's okay. So let's try that again. The limit as x approaches 1 of what should I be writing on top here? X minus 1. I was looking at 1 for x for some reason. And if y is negative 1, we have negative 1 times x. So negative x plus 1. And that actually also simplifies. We can write this as the limit as x approaches 1 of x minus 1 divided by negative 1 times x minus 1. The x minus 1s again divide to 1. So we're left with the limit as x approaches 1 of 1 over negative 1, which is just negative 1. They're not the same. Limit doesn't exist. Can I write words? Maybe. So our limit as x comma y approaches 1 comma negative 1 of x plus y divided by xy plus 1 does not exist. I will say from experience, professor, instructor, whatever his title is, Lee typically does not ask you any limits that are hard to show they exist. Like it might be an easy one where you plug it in and it turns out nice, or you might factor something easily. But like the thing I'm about to show you, I don't think I've ever seen instructor Lee talk about or assign problems for. I don't know about var. I would, if I had to guess, I would imagine he'd probably have you do this next stuff. That's my gut place. That's not for any good reason other than he seems like the kind of guy that would like to ask you hard questions. So I mean, that's just my impression of him. So let's look at this example. The limit as x comma y approaches, and not like purposely hard or tricky, like he just like, I don't know, he has high expectations, I think. Limit as xy approaches 0, 0 of 2x squared y divided by 3x squared plus 4y squared. Certainly a 0 over 0 type. And if we try a bunch of different paths, they're all going to come out to be 0. So like if we tried y equals 0, we would get the limit as x approaches 0. Let's make it simple. We're going to get 0 divided by 3x squared, which is going to be 0. And any other path you might try is still going to give you a 0. If you tried something like y equal to x, same result. You're going to get the limit as x goes to 0 of 2x cubed over 3x squared plus 4y squared. So that's going to be the limit as x goes to 0 of 2x cubed over 7. Sorry, that's a 4x squared, apologies. Over 7x squared. That's the same as the limit as x goes to 0 of 2x over 7, which is going to be 0. And you could keep doing this forever, and you would always get 0, which would eventually make us think, well, maybe the limit actually exists and is equal to 0. So how do we show it? That's the hard part. So, yeah. If the limit's 0, so in fact, let's write some words here. So to show that the limit of some function is some number, in this case 0, what we're going to do is we're going to consider the distance between the function and the value of 0. And the idea is that as xy approaches 0, 0 from any direction, the distance between the function and the value of 0 should get really, 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 really small. So here's our distance. The distance between two things is the absolute value of their difference. Right? Because we typically think of distance as a positive thing. So when you're measuring the distance between two things, if the value comes out negative, you take the absolute value of it to make it positive. Okay, so this is going to be the same as, well, just our function, 2x squared y divided by 3x squared plus 4y squared minus 0, which we don't need to write. And now is where things get tricky. You have to have some intuition about what to do. So here's what I point out. Anything squared or to an even power is already always positive, so it doesn't need to actually be in the absolute value. So here's the trickery that I'm going to employ first. I'm going to write this as 2x squared over 3x squared plus 4y squared. That's already always positive, right? Everything is squared. Multiplied by the y that's still left inside the absolute value there. Seems not super necessary, but it's going to help us just write things out. So now here's the part that I think is something that's not obvious without having done it before. And that's sometimes what you need. You need to have done it before to know how to do it in the future. So what we're going to say here is, well, check this out. 2x squared is definitely less than 3x squared. Right? Whatever x is. 3 times x squared, which is positive, is always going to be bigger than 2 times x squared, which is positive. And then if I add 4y squared, still true. 2x squared is definitely less than 3x squared plus something that's non-negative. And then what we can say is that this expression here, this is definitely going to be less than 3x squared plus 4y squared over 3x squared plus 4y squared times the absolute value of y. But 3x squared plus 4y squared divided by 3x squared plus 4y squared is 1. So we've got an inequality. In fact, I've got a compound inequality because this absolute value, you know what's always bigger than? Or equal to? 0. So here's what we can say. 0 is less than or equal to the absolute value of our function, 2x squared y over 3x squared plus 4y squared. And that is definitely less than or equal to the absolute value of y. And now you know what we're going to do? We're going to use the squeeze theorem. Right? If you have something in between two other things, if you take the limit of those things and they both have the same value, then the middle thing also gets squeezed to that value. So notably, the limit as y approaches 0, I should say x comma y approaches 0, 0, apologies, of 0 is certainly equal to 0. And the limit as x comma y approaches 0 comma 0 of the absolute value of y, well, if y is getting closer to 0, the absolute value of y is getting closer to 0. So that means the limit of that's 0, the limit of that's 0. So the limit of the middle part has to be between 0 and 0. Oh, it's got to be 0. So we can say that by the squeeze theorem, which I'm going to abbreviate because I'm out of room. By the squeeze theorem, the limit as x, y approaches 0, 0 of the absolute value of 2x squared y over 3x squared plus 4y squared has to be 0. And the limit of an absolute value is 0, then the limit of the original thing is also equal to 0. So this limit is 0. And that's usually how we do these, which is, right, you can see it's kind of a giant, terrible pain, right? Like that is not something typically someone's probably going to ask you to do on the test. Not that that's a guarantee, but it's usually unlikely. I think we should do one more, but before we do one more, let me pause for questions or comments or thoughts. So I'm not saying the absolute value of y is equal to 0. I'm saying that if we take the limit as x, y gets closer to the point 0, 0, well, that means y is approaching 0. So we're really just plugging in the 0 that y is approaching for the absolute. So I could have written it as the absolute value of 0 plugged in for y, and then the absolute value of 0 is 0. But we're really just saying, just like with most limits, if you can plug in the value that your thing is approaching, we do, and we get the number that it's equal to. Yeah.
I'm kind of confused, just like with the whole distance thing.
Uh-huh.
Can you just explain?
Sure. So it's kind of, the idea is that to show a limit exists, there's kind of, and this is something that doesn't get covered in 17A or in this class really, but there's a more like precise definition of a limit. It's usually something called a delta epsilon proof, where you prove that if your x is close enough to the thing it's approaching, then your function is close enough to the value it's supposed to be. But the blanket kind of idea is that we're really just saying to show, in fact, let me write it, I'll write it over here more. To show, and I'll use some 17A notation, to show that the limit as x approaches a of f of x is equal to some L, what we're really just trying to show, we want to show that the distance between the function and the limit approaches 0. Because if the distance between these two things are 0, that means that the function is getting closer and closer and closer to the limit value. That's the whole thing. That's it. So let's do one more. Yeah, we can do one more. Let's look at this one. Yeah, we got enough room. Let's move that cursor out of the way. So let's say we want to find the limit as x comma y approaches 0 comma 0 of xy divided by the square root of x squared plus y squared. And we're not going to go through the whole pretending that we don't know what it is, and we have to try. It exists. We're just going to show it exists, and it's going to be equal to 0. We know it's going to be equal to 0 because we pick a path, right? So if someone tells you a limit exists, then you can just pick one path to find the value. If we pick the path, gosh, if I can stop, it's sounding so terrible. If we pick the path x equal to 0, we're left with the limit as y approaches 0 of 0 on top and the square root of y squared on the bottom. And then it's the limit of 0, which is 0. Happens a lot. Okay. So now we're going to show this exists. So we want to show that this distance between f of x, y, and 0 gets small. So our distance is the absolute value of f of x, y minus 0, which then we're actually going to write the function xy over the square root of x squared plus y squared minus 0. And then the job is to essentially break this up into something so you can get an inequality somewhere. Usually you're looking for something in the numerator being less than something in the denominator. So let's break this apart. I'm going to write this as the absolute value of x times the absolute value of y. The square root does not need any absolute values around it because it's already spitting out positive things. If the square root of x squared plus y squared is already positive, so we don't need the absolute values around it. So let me go this way. Note that the absolute value of y is equal to the square root of y squared. We talked about that before? Can't remember if I said that in this class or a different class. But it is true that the absolute value of a variable is equal to the square root of that variable squared. But then the square root of y squared is definitely less than or equal to the square root of x squared plus y squared. Right? That thing there has to be bigger than or equal to that thing there. If x is 0, they're equal. If x is anything else, this thing is bigger. For sure. And I would probably, so I like to do it a slightly different way. Instead of just saying this part is less than or equal to that, I like to go in this direction and say that means that the absolute value of y divided by the square root of x squared plus y squared has to be less than or equal to 1. Right? If a number is less than another number, then that number divided by the other number has to be less than 1. And bigger than or equal to 0 because, right, everything here is non-negative. So then we're going to take this expression and we're going to rewrite it as our absolute value of x times the absolute value of y over the square root of x squared plus y squared is certainly less than or equal to this part times my absolute value of x. And it's certainly bigger than or equal to 0. Has to be. Has to be bigger than or equal to 0, right? It's an absolute value. And then, well, the limit of this part, so yeah, I should write more words. But then what we get to say is, okay, yeah, the limit as x comma y approaches 0 comma 0 of 0, well, limit of a constant, still a constant. And certainly the limit as x comma y approaches 0 comma 0 of the absolute value of x is definitely equal to the absolute value of 0, which is 0. And then again, by the squeeze theorem or sandwich theorem, whichever way you like to say it, the limit as xy approaches 0, 0 of the original thing we started with, which was the absolute value of xy over the square root of x squared plus y squared is equal to 0. And I should say more here, right? So if the limit of an absolute value of something is equal to 0, then the inside stuff has to go to 0, right? It can't go anywhere else. So then we can say that the limit as x comma y approaches 0 comma 0 of the inside stuff without the absolute values, which is what we started with, is also indeed equal to 0. It's kind of a lot. Yeah. So in the previous one, I had a different thing going on. So in the previous one, where'd you go? Sorry, where's my notes? Everywhere. So in the previous one, so in the previous one, I had a 2x squared times y, and that x squared is already always positive, so I didn't need to keep the absolute values around it. Whereas in this one, I had x times y in the numerator, and both of those, right, x on its own could be positive or negative. y on its own could be positive or negative. So I still needed to retain the absolute values around them. But I wanted to break them up. So I didn't just write absolute value of x times y. I wrote the absolute value of x times the absolute value of y. But it is the same, right? The absolute value of a product is equal to the product of the absolute values. Because whether you take the absolute values, take them first and then multiply them together, or multiply them together first and take the absolute value, the result's still always going to be non-negative. It doesn't really matter if you do it first or after.
So,
Right, because I'm saying that this part right here is less than or equal to 1, right? Just that's exactly that part right there. And so then this whole expression is less than or equal to the absolute value of x times the thing that this is less than. If you prefer, and you might prefer doing it the other way, let me just show you. If I had done it this way instead, where I'd started with the absolute value of x times the absolute value of y divided by the square root of x squared plus y squared, and just had said, oh, well, I just said my absolute value of y is less than or equal to the square root of x squared plus y squared, and this is less than or equal to the absolute value of x times the square root of x squared plus y squared divided by the square root of x squared plus y squared. And then those cancel and give me the absolute value of x. Either way is fine. I just thought I would show it a slightly different way at the time. Yeah.
Numbers.
Yeah, I mean that's probably too large of a thing to say, but typically when you're doing this, you are starting with an absolute value of some stuff. So you kind of have to work from there. Really, the way to kind of to learn this is to try to practice it. Right? Like I can show you lots and lots of examples, but until you do it for yourself, I think it's hard to kind of grasp what's going on. I think let me double check here. I know these problems weren't assigned, but nope, I don't have the paper with me. I thought I did. Sorry. I'll look in the textbook and see. I think there's a couple of problems where the limits do exist and they kind of require this process. It's probably good practice. It's probably not necessary practice if you're in Lee's class, to be perfectly frank. Unless he says something else. But last quarter when he taught this class, he specifically said like he wasn't going to ask ones like that. So he might have changed how he does things, but last quarter that's how he did it. All right. What else? So that's enough limits. Where are we going next? Actually, before we go somewhere next, I wanted to show you one thing. So last class I was talking about the saddle and like how the level curves are hyperbolas. I just wanted to kind of show you a better picture. So here is a saddle. Oops, don't zoom in like that. Sorry. Oh my gosh. What? Give me there we go. Here's a saddle. It's essentially y squared minus x squared, except I divided it by 2 just to make it not so tall. And then here are our level curves, different. So like here's z equal to 1. If you look at that, it looks exactly like a hyperbola, right? This curve here and that curve there, that's your z equals 1 level curve. So at that height, the curve is just that hyperbola. Or you could say the plane at a height of z equal to 1 intersects the surface in that hyperbola. In fact, if we drew the plane, give me a nice color here. Why would you pick that color? I don't know how, like, what the process is for how Desmos chooses a color for you, but right, so you can see, oh yeah, look, at a height of z equals 1, you're exactly getting that hyperbola and nothing else. Kind of neat. And then if you go up higher, right, you get the next one, and so on and so on. And it is kind of interesting to see that at z equal to 0, right, our level curve is this crisscross absolute value thing, which is kind of funky looking, but definitely is what you get in the XY plane. So I just wanted to kind of show you a better picture of that because I thought I didn't do a great job of drawing it last class. Okay, we got 5 minutes left. Here's where we're going. We're going to start talking about partial derivatives, which are super straightforward once you know what's going on. Like they're probably one of the easier things we do in this class, to be perfectly honest. Yeah, let's look at this example. So let's say we have the function f of xy equal to 9 minus x squared minus y squared, which to me always looks like kind of like a mountain. It's an upside down paraboloid. Looks like this. And we want to look at the point on the surface 1, 2, 4. So we're going to go 1 in the x direction, 2 in the y direction, and then 4 in the z direction. About right there. So that level curve there, that circle, is at a height where z is equal to 4. And if we plugged in z equal to 4, you get the equation of a circle, x squared plus y squared equal to 5, which would have a not lovely radius. So now here's the question. If we're standing on this hill, mountain, whatever, and if we move in the positive x direction, what's the slope of the surface? So essentially we're asking, if I move in this direction here, if I move in the x direction and hold y constant, right? If you're moving in the x direction, you're not moving left or right, you're holding y constant. In this particular example, y is equal to 2, because we're starting at the point 1, 2, 4. The y value is 2, and that's not changing. So we move in this direction, specifically that way. What's the slope of the surface? Or what's the slope of the line tangent to the surface to this curve that we're cutting? Well, it's really easy to find. We're going to take the partial derivative with respect to x, because x is the only thing that's changing. Y is staying constant. So the derivative of 9 is 0. The derivative of x squared is 2x. Let me ask you a good question here. What's the derivative of something that isn't changing? Right. Something that isn't changing is also known as a constant. So the derivative of a constant is 0. The derivative of something that isn't changing is 0. Y isn't changing. Y squared isn't changing. What's the derivative of y squared? 0. So our partial derivative with respect to x is going to be negative 2x. And if we plug in the value of x, which is 1, the partial derivative evaluated at 1, 2, 4 is negative 2 times 1, which is negative 2. So if we move in the positive x direction out towards you, the slope is negative 2. For every 1 I move forward, I move 2 down. In a similar way, we can ask what the derivative or the slope is in the positive y direction if we move to the right instead of moving forward. So in the positive y direction, again, I want to make it super extra clear. If we're moving in the y direction and only in the y direction, no other variable is changing. X isn't changing. So our partial derivative with respect to y, which you say fy, or you could also write it as del f del y. It's not a d, it's a del because it's a little curlier than a d. No one is going to notice if you write a d. But it is technically a del. If you're taking a partial derivative, meaning your function has more than one variable, it's a partial derivative and we say del, not d. But our del f del y is going to be 0 minus 2y. And if we plug in our point, our del f del y evaluated at 1, 2, 4, we're going to plug in a positive 2 and get a negative 4. Also, here's a cool picture of what's going on. Maybe. There it is. So here is that tangent line in the x direction, right? If you're on the curve at the point 1, 2, 4, or on the surface, and you move in the positive x direction out towards you, the slope is definitely negative 2. Now, here's what's kind of weird. If you went backwards instead and moved in the negative x direction, the slope would be positive 2, because then you'd be moving up instead of down. So on a surface, if you turn around 180 degrees, it changes the value of your derivative to the opposite sign. We'll talk more about partial derivatives on Monday. But the thing you need to know about them really is that to take a partial derivative, you just do it like a regular derivative, but you pretend like the variable that doesn't matter as a constant and treat it as such.